Welcome back, students, to the second part in our discussions on the topic friction. In my previous class, I told you that friction is an opposing force that comes into play when one body actually moves, that could be in the form of sliding or rolling, or even tries to move over the surface of another body. The force of friction is the force that develops at the surfaces of contact of two bodies and impedes their relative motion. We had discussed about the origin of friction. According to the old view, roughness of surfaces is the cause of friction, while according to the modern view of friction, it arises on account of strong atomic or molecular forces of attraction between the two surfaces at the points of actual contact. We may classify friction into two types: external friction and internal friction. External friction, which arises when two bodies in contact with each other try to move or there is an actual relative motion between the two. The external friction is also called contact friction. Internal friction, which arises on account of relative motion between every two layers of a liquid. Internal friction is also referred to as viscosity of the liquid. Further, external friction is of three types: static, limiting and kinetic friction, about which we had discussed in full detail in our previous session. So let's quickly go to the first topic of discussion for today, and that is angle of friction. The angle of friction between any two surfaces in contact is defined as the angle which the resultant of the force of limiting friction, as you can see in the picture, it is marked F limiting. So the resultant of the force of limiting friction and normal reaction R makes with the direction of normal reaction. It is represented by theta, and that is quite properly marked in the diagram. So angle theta represents angle of friction. Now in the figure, CA represents the normal reaction R, which balances the weight W, that is mg, of the body. CB represents the limiting force of sliding friction when the body tends to move to the right. Now we need to complete the parallelogram CALB and then join CL. This represents the resultant of normal reaction and the force of limiting friction. So by definition, angle ACL is equal to theta, that is the angle of friction. So angle ACL, that is the angle of friction. The value of angle of friction depends on the material and nature of the surfaces in contact. Now considering the triangle ACL, in this triangle it is a right angle triangle, so tan of theta will be equal to perpendicular by base, so that is equal to AL divided by AC, which is further equal to CB divided by AC. So tan of theta is equal to F limiting divided by R, and that is equal to mu according to the laws of limiting friction. Hence, mu is equal to tan of theta, that is coefficient of limiting friction between any two surfaces in contact is equal to tangent of the angle of friction between them. Let's mark it as equation number A. Angle of repose or angle of sliding. Angle of repose or angle of sliding is defined as the minimum angle of inclination of a plane with the horizontal, such that a body placed on the plane just begins to slide down. It is represented in the diagram as phi. Its value depends on material and nature of the surfaces in contact. Now in the figure, OB is an inclined plane such that a body placed on it just begins to slide down. Angle BOA BOA, that is equal to phi, and that is angle of repose. Now, as you can see in the diagram, the various forces involved are weight W, that is equal to mg of the body, acting vertically downwards, normal reaction R acting perpendicular to OB, force of friction, that is marked F, acting up the plane OB. Now mg can be resolved into two rectangular components, mg cos phi opposite to R and mg sin phi opposite to F. Obviously, in equilibrium, F will be equal to mg sin of phi and R will be equal to mg cos of phi. So if we divide these two equations, we will get F by R equal to mg sin of phi divided by mg cos of phi. So you can cancel out mg. So we are left with F by R equal to tan of phi. Further, F by R is equal to mu. So we can write down, therefore, mu equal to tan of phi. Hence, coefficient of limiting friction between any two surfaces in contact is equal to the tangent of the angle of repose between them. Let us mark this equation as equation number B. Now, very quickly, let's go back to equation number A. According to equation number A, mu is equal to tan theta, where theta represents angle of friction. But according to equation number B, mu is equal to tan of phi, where phi represents angle of repose. So we can write down mu equal to tan of phi, and that is also equal to tan of theta. This can be written by combining equations A and B. So therefore, we can write down theta to be equal to phi. This means that angle of friction is equal to angle of repose. Acceleration of a body down a rough inclined plane. Now, when a plane is inclined to the horizontal at an angle theta, which is greater than the angle of repose, the body placed on the inclined plane slides down with an acceleration a. As it is quite clear from the diagram that R is equal to mg cos theta. Normal reaction R is equal to mg cos theta. So net force F down the inclined plane, net force on the body, this body down the inclined plane, that is marked as F, will be equal to mg sin theta minus F. Capital F represents friction, which is further equal to mu into R, where mu is the coefficient of limiting friction. So let's quickly write down the equations. We can write down R, that is normal reaction, to be equal to mg cos of theta, as it is quite clearly visible in the diagram. And net force on the body, if we represent it by small f, that will be equal to mg sin of theta minus force of friction, as you can see in the picture. So now we can write down F, which is equal to mass into acceleration, to be equal to mg sin of theta minus force of friction. Force of friction is given by mu into R. Therefore, m into A will be equal to mg sin theta minus mu, and as you can see in this equation, R is equal to mg cos theta. So now we can write down, instead of R, mg cos theta. So therefore, m into A, if we take out mg as common, we will get sin of theta minus mu cos of theta. and cancel out m, and therefore we get the expression for acceleration as g times sine theta minus mu cos of theta. This is the expression for acceleration. And obviously this implies that acceleration is less than acceleration due to gravity. Acceleration of a body down a rough inclined plane is always less than acceleration due to gravity. Now it is to be noted that when a plane is inclined to the horizontal at an angle theta, which is less than the angle of repose, when a plane is inclined to the horizontal at an angle theta, which is less than the angle of repose, then the minimum force required to move the body up the inclined plane will be given by F1 equal to mg sine of theta plus force of friction, and which is further equal to mg sine of theta plus mu cos of theta. Further, the minimum force required to push the body down the inclined plane. The minimum force required to push the body down the inclined plane, if it is represented by F2, then that will be equal to force of friction F minus mg sine of theta. So that may be further written as equal to mg mu cos theta minus sin theta. Work done in moving a body over a rough horizontal surface. We know that friction always opposes the relative motion between any two surfaces in contact. Hence, some work has to be done in moving a body over a rough horizontal surface. As it is clear from the figure, on a level track, the weight mg of the body is balanced by the normal reaction. So we can write down R to be equal to mg. To move the body on a level track, we have to apply a force P, which is at least equal to the force of friction F. I repeat, to move the body on a level track, we have to apply a force P, which is at least equal to the force of friction F. That is, P is equal to F. Under the action of the applied force, suppose the body moves through a distance S. So as work done is equal to force into distance, or force multiplied by displacement. So we can write down W to be equal to PS, or which may also be equal to F into S. Now we know that mu is equal to F by R. Therefore, F is equal to mu into R. Therefore, work done W will be equal to mu RS, which is further equal to mu, and R is equal to mg. So mu mg s. Knowing mass of the body, distance moved, and the coefficient of friction, we can calculate the work done in moving the body over a rough horizontal plane. Obviously, it would depend upon weight of the body, material and nature of the surfaces in contact, and the distance moved. Work done in moving a body up a rough inclined plane. Suppose m is the mass of a body that has to be moved up a rough plane AB, inclined to the horizontal at an angle theta. The various forces involved are weight mg of the body, that is acting vertically downwards, normal reaction R, acting perpendicular to the plane AB. Force of friction F, as you can see it is marked F, acting down the plane AB as the body moves up the plane. The weight mg can be resolved into two rectangular components, mg cos theta opposite to r and mg sin theta down the plane AB, where P is the force required to be applied up the plane AB. Under the action of this force, suppose the body moves through a distance s up the plane. Suppose distance travelled is given by s. Then work done is equal to P into S, and P, if you can check the diagram, P should be equal to how much? P is equal to mg sin theta plus F. Mg sin theta plus F, which is further equal to mg sin theta plus mu into r. So work done will be equal to mg sine of theta plus mu into r multiplied by s, where mu is the coefficient of friction between the two surfaces in contact. We already know that r is equal to mg cos theta. R is equal to mg cos theta. So we can further substitute and get the final expression for W as mg. If we take out mg as common, we will get sin theta plus mu cos theta multiplied by s. So knowing m, theta, s and mu, we can calculate work done in moving the body up a rough inclined plane. Now one thing is to be remembered, that in moving a body over a rough horizontal surface, work has to be done only against the force of friction, which is a function of normal reaction or weight of the body. However, in moving a body up an inclined plane, work has to be done against friction as well as component of weight pulling the object down the inclined plane. Now a very important topic of this discussion. Friction is a necessary evil. Two contrasting terms have been clubbed together. How a certain quantity be both necessary as well as act as a disadvantage. It is a necessity because we cannot do without it. At the same time, it is an evil because it involves unnecessary waste of energy. So let's begin with the necessity part, that is the advantages of friction. Walking will not be possible without friction. To enhance friction, it is advisable to use shoes with rough sole while walking on slippery floors. For a similar reason, crutches are provided with rubber tips at their bottom to provide sufficient friction. While walking, our foot pressing the ground will only slip if there is no friction. That is why it is so difficult to walk on a wet surface, or there is a tendency to slip on the floor if we accidentally step on a peel of banana, or some soap solution is falling on the ground, because due to the absence of the required amount of frictional force. Friction is necessary for a proper grip on the surface. No two bodies will stick to each other if there is no friction. Brakes of the vehicles will not work without friction. The ridges in the skin of our fingers and palms enable us to grasp and hold objects due to friction. Nuts and bolts for holding the parts of machinery together will not work in the absence of friction. Writing on blackboard or on paper will also not be possible without friction. To prevent patients being uncomfortable in bed, rubber sheets with spongy undersurfaces are placed over mattresses. The friction between the spongy undersurface and the mattress prevents the rubber sheet from slipping and wrinkling. The transfer of motion from one part of a machine to the other part through belts will not be possible without friction. Adhesives will lose their purpose in the absence of friction. Cleaning with sandpaper will not be possible without friction. And so on. So many things can not be accomplished in the absence of frictional force. So it becomes a necessity. As you can see in the picture, there are certain benefits of friction. Some common benefits. Like you can see striking a matchstick, spiked shoes of cricket players, driving on automobiles, or writing on paper, as we were discussing right now. Now comes the disadvantage part. Friction always opposes the relative motion between any two bodies in contact. Therefore, extra energy has to be spent in overcoming friction. Thus, friction involves unnecessary expense of energy. It means output is always less than the input. Friction causes wear and tear of the parts of machinery in contact, thus their lifetime reduces. Frictional forces results in the production of heat, which causes damage to the machinery. Due to friction, engines of automobiles consume more fuel, which is a money loss. So as you can see in the picture also, there are a couple of disadvantages of friction that has been shown. A very common disadvantage of friction is forest fire. So about 20% of the petrol used in an automobile is used up to counteract friction in the engine and in the driving. On the contrary, if friction were totally absent, we would not get an automobile to go anywhere. We could not walk or even ride a bicycle. We would not be able to hold a pencil, and if we could, the pencil would not write. Nails and screws would not work. The knots in woven clothes would untie themselves. So we can see that it acts both as an advantage as well as a disadvantage. So it is referred to as a necessary evil. So obviously, where it is acting as an advantage, we would be requiring to devise methods to increase the amount of friction. On the other hand, where it is acting as a disadvantage, we would be trying to figure out methods so as to reduce the amount of friction. Let's begin with that. Some of the ways of reducing friction. By polishing. Polishing makes the surfaces smoother, therefore friction reduces. By lubrication. Lubricants like oil, grease fill up the irregularities of the surfaces, making them smoother. Hence, friction decreases. By proper selection of materials. We know that friction depends on nature of material of the surfaces in contact. The surfaces of moving parts of machines in contact can be lined with materials having low coefficient of friction. On the same basis, tires are made of rubber. This is because friction between rubber and concrete is much less than friction between iron and concrete. Another method would be by streamlining. Friction due to air is considerably reduced by streamlining the shape of the body. That is, it should be sharp in point, which is moving through air. For example, the shape of jets, aeroplanes, fast-moving cars are streamlined. By using ball bearings. Ball bearings used in ceiling fans, bicycles and vehicles help to reduce friction. Similarly, a thin cushion of air maintained between solid surfaces in relative motion is another effective way of reducing friction. Let's talk about some cases where we will be requiring friction. So obviously, we should also be aware of methods so as to increase friction. We are able to walk because of friction. All of us know how difficult it is to walk on ice when force of static friction is small. It is impossible to start a car on a very slippery road. On an ordinary road, friction between tires and road converts rotational motion of the wheels into a rolling motion and provides the necessary external force to accelerate the car. Kinetic friction is important for quickly stopping relative motion, though power is dissipated in the process. So, some of the ways of increasing friction, like for example, on a rainy day, we throw some sand on the slippery ground. This increases friction between our feet and the ground. So, the chances of slipping reduce. Similarly, sand is spread on tracks covered with snow. Force of friction between the wheels and the track increases and driving becomes safer. In the manufacture of tires, synthetic rubber is preferred because its coefficient of friction with the road is larger. Proper threading of the tires also increases the force of friction between the tires and the road. Spikes are provided in the soles of shoes used by players and athletes to increase friction so that they get a firm grip on the ground. Gymnasts apply a coat substance on their hands, like for example chalk powder, to improve their grip. So, though friction opposes motion, yet in certain cases, friction is also the cause of motion. For example, when a person pushes the ground backwards, the rough surface of the ground reacts and exerts a forward force due to friction, which causes the motion. Without friction, person would slip and shall not be able to move. In cycling, rear wheel moves by the force communicated to it by paddling, while front wheel moves by itself. Therefore, like in walking, force of friction on rear wheel is in the forward direction. As front wheel moves by itself, force of friction on front wheel is in the backward direction. However, when paddling is stopped, both the wheels move by themselves. So, the force of friction on both the wheels is in the backward direction. Thus, without friction, motion cannot be started, stopped, or transferred from one body to the other. That should be all for today. Thank you.